Thank the ICTS and all the organizers. And a few of you might have heard of this talk before, so I probably apologize for that. So this talk is, the careful audience will see that this talk is kind of connected to Rizwan's previous talk. And our background are essentially the same, actually. So I first talk about Ivic's work, and then I state my results, and also the method and the proof. So we're going to work with Maass-form L functions, and the space we're talking about is also the modular surface. It's H modulo SL2Z, and we're concerned with cast forms, and we are looking mainly at this Laplacian eigen value, and we're going to take it to be again 1/4 plus TF squared, and this TF squared will be our main parameter here. Okay, and if you want to talk about Maass-form L functions, then we need this Fourier coefficients, and in general we just expand it in this Fourier expansion, and this rho Fn will be our Fourier coefficients. All right, and we are also going to make some arithmetical assumptions. First of all, it's the Hankel operator defined in this way, and we're going to assume these f's are Hankel eigenfunctions, and the Hankel eigenvalues will be denoted by lambda Fn. And also another simple condition is this parity condition. We're going to assume f being either even or odd. So you have this root number epsilon f being 1 or -1. And we know that this lambda f and the rho f are proportional. So sometimes I'll just call lambda f also as Fourier coefficients. All right, and these are the conditions for, if you assume these conditions, you have these two identities. Okay, and we're going to take this capital B to be an orthonormal basis of usually it's even Hankel cast forms, and this L function will be defined by this Dirichlet series and its analytic continuations. And in Ivic notation, he usually write it as H, and here H stands for Hankel series. But I'm going to use the more standard notation as L function. And we know that it has Euler product, and these are all due to Hankel, at least in the holomorphic case. And we also have this functional equation. All right, and we know that if the root number is -1, then the L function, the central L value will be trivially 0, and if it's 1, then it's always non-negative. This is due to Katok-Sarnak. And for this reason, we're going to usually we're going to assume that all these f's are even, namely this epsilon f are all +1s. Okay, and now let's talk about what we're going to study. So first of all, let's introduce this so-called harmonic weights, and this doesn't really matter. You can consider it as 1 because it's just between some epsilon powers of TF. So you can usually assume it, pretend it to be 1. So we're going to consider this MKT, M capital KT, and we're going to sum over these mass forms with parameter t, small t, being smaller or equal to capital P. And we're going to average this central value of the case power of these central values and weighted by these harmonic weights. And also we have this Eisenstein, or you can say Riemann zeta two-case moment. This comes from the Eisenstein series. And also we're going to consider this a little bit more complicated MKTH defined this way. So this TF, small tf, will be centered at, will be on an interval centered at T, capital T, and with window length capital H, defined in the same way. Only that this is a short window version of the previous case moment. And we're going to take this H as small as T epsilon, okay, and take it to be as large as say T over 3. And if H is T over 3, then this is actually a dyadic interval, and you can go back and forth between this case and this the non-interval case. All right. Okay, then I'm going to talk about several results of Ivic. This is a photo of him I took from the website. And the first result is in the paper of Ivic in 2002. And he made this moment conjecture. So if you consider the case moment on the long interval, then you will have a main term as t squared times a polynomial of log t. And here this polynomial is of degree k squared minus k over 2, right? And plus an error term. And if you want this to be really an error term, you want this ck to be smaller than 1. Okay, this is Ivic's moment conjecture. I would call it the weak conjecture, because he also conjectured that this ck will be all 0. Namely, you will have this error term t to the 1 plus epsilon. And you should know that there's a square root rule here, because the main term is roughly t squared, and the error term is the square root of t squared, roughly. So the base is square root rule. This is so-called, I would call it the Ivic moment conjecture. And of course, there are also many other moment conjectures by the work of Conrey, Farmer, Katin, Rubinstein, and Slace in 2005. And probably the conjecture was formulated earlier, but the paper was published in 2005. And they consider various families, and according to the symmetry type, there will be a unitary type, symplectic type, and orthogonal type. And for the unitary type, you can consider a typical example is this Riemann zeta function on the critical line. And also you can consider quadratic characters, then this will be symplectic type. And also if you consider the holomorphic case, so this is of level n and the weight k. And if you fix one of them and order the other, then they will all they are conjectured to be orthogonal type. And the main term was predicted by the so-called random matrix theory. I'm not going to expand this. And in all the conjectures, the error term will be obey the square root rule. Okay, and so you can consider this Ivic strong moment conjecture for mass forms as an analog of Conrey, Farmer, Katin, Rubinstein, and Slace conjecture. So you can fit into this framework. And in our case, it's orthogonal type. And if you recall earlier, so in our case moment, there will be a two-case moment of the Riemann zeta function. Okay, of course there are some spectral weights here, some harmonic weights here, but you can ignore that. So let me take this as a very typical example. And the moment conjecture would read like this. So the main term will be capital T times some 2k k squared degree polynomial of log t, and plus the error term of size square root of t. This is the moment conjecture for the Riemann zeta function. And in the case k equal to 1, there's a long history, and currently the best error bound will be t to the 1.31 ... And you should know that this actually for k to 1, the conjecture will be t to the 1/4, not t squared, t square root of t, not t to the 1/2. So this is k equal to 1 case. And for the k equal to 2 case, the currently best error bound will be t to the 2/3. And also there's a long history here. So actually Ingham gave the leading term of the main term. And about half a century later, Hisbron actually gave a genuine asymptotic. And then Zavorotny, he proved it to be t to the 2/3 plus epsilon, and then Ivic-Motohashi proved that epsilon to this 8th power of log t. And this is the history of k equal to 2. And for k greater or equal to 3, even an upper bound is still wide open. So this is t to the 1 plus epsilon. This is a very simple consequence of the asymptotics, right? And currently, the only known result for the higher degree case is k equal to 6, and Hisbron proved that in this case it will be t squared, the upper bound. It has the upper bound t squared. And one thing you should know that if you have this upper bound, then the integral moment of the Riemann zeta function can actually be absorbed into the error term. So in this sense, the Maass-form should actually dominate in this case moment, in this MKT. So you can absorb this two-case moment of the Riemann zeta into the error term, if you assume this upper bound. Okay. These are some backgrounds for the moments conjecture, especially for the Maass-form case. And then I'm going to talk about I'm going to talk about the Ivic conjecture and the known results. In the k equal to 0 case, this is more or less the Weyl law. And of course, Weyl law usually is proven for both even and odd forms. The currently best result is due to Cauchy-Schwarz proves the error term to be bounded by t over log t. Okay, and for k equal to 1, Ivic and Jutila proved it to be gave an upper bound t log epsilon t. And when k equal to 2, Motohashi proved it to be like t to the t times 6th power of log t. And for k equal to 3 and k equal to 4, these are due to Ivic and also Kuznetsov. And they prove that this C3 is 1/7 and C4 is 1/3. Okay, so in these two cases, they didn't get didn't get the strong Ivic conjecture. So they proved it to be 1/7 and 1/3. And some audience asked a question about Kuznetsov formula, right? In the K equal to 4 case, you can actually check Ivic paper. So there are actually some errors in Kuznetsov original paper, but Ivic correct those errors. Okay, anyway, so let's go. For K greater or equal to 5, this is still wide open. So, but there are upper bounds in some other cases. For example, usually for holomorphic cases with levels and weights due to Kira-Young and Bloomberg-Kahn and Kahn. Okay, so in this paper, in this talk, I will talk about the K equal to 3 case. Actually, I'm going to prove that this C3 is equal to 0. Okay, and another related work of Ivic is his Lindelof-on-average bound. So, so in this case, we can still consider this M3 TH. Okay, this is the short interval case, and he proved that upper bound H times T to the 1 plus epsilon. This is indeed a Lindelof-on-average bound. If you take this L to be bounded by T to the epsilon, then you have this H times T to the 1 plus epsilon. And then you can ignore the Eisenstein theory contribution. This is always non-negative. And then you have this upper bound for mass L functions. And also we know that it's non-negative. So a simple consequence is the wild type subconvex bound. This is a well-known result of Ivic. Okay, so let's talk about some results of mine. So first of all, if you consider the cubic moment on short interval, and you can take this H to be as before from T epsilon to T over 3, and then we have this asymptotic. So the error bound will be T to the 1 plus epsilon here, and the main term will be a integral of this K times a cubic polynomial of log K. And this polynomial will be very explicit. I'll explain it a bit later. And a direct consequence of this is the Ivic Lindelof-on-average bound. So you can consider it as a refinement of the upper bound. This is asymptotic. And a second theorem is that if you insert this weight, so this weight essentially centered at it's a bump function, essentially centered at T and with window length M. Okay, and again you can take this M as small as T to the epsilon. Then you have this asymptotic, and you have this MT times cubic polynomial of log T, and the error bound is still T to the T1 plus epsilon. And also this implies Ivic Lindelof-on-average bound. Okay, so now let's come to the long interval case. So in this case, M3T, this is what we defined before. We can prove that you have a main term and the desired error term by Ivic. The error bound will be T to the 1 plus epsilon. And this is indeed the strong Ivic conjecture. And as for the main term, this polynomial and this is P3 and P3 natural, they are connected via this identity. So our focus, of course, will be on the error term. So I'll explain how to bound the error term by this t plus t to the 1 plus epsilon.
Yeah, maybe if you try to switch off the video, that may help.
All right, so let me say a bit about this formula, about this lemma. So essentially speaking, we're going to average this M3 natural. So I'm going to replace this T by K and then average over K. And this is what I do. And the interval that I average will be from T minus H to T plus H. All right, so it's like moving a bump function along an interval. You can consider it like that. And the running error, so in this case, we can approximate the characteristic function, and the running error will be m times t to the 1 plus epsilon. Okay, so if you want the best error bound, then you need to take this m to be t to the epsilon. This is the best we can get. Mute your video. Okay, yeah, sure. Let me. Okay, maybe, yeah, sure. Okay, let's continue. So if you want a t to the 1 plus epsilon, then you need to take this m as small as t to the epsilon. But this is usually very hard. But fortunately, in our case, we can do this. And one thing you should know is that Xiaoqinli obtained t over log t. So in his paper, he used another method. So you cannot achieve this by this unsmoothing lemma. Okay, so anyway, so what we're going to do is, all we do is that we replace t by k in m natural km, and then do the average. Okay, and then you get this the m3th without the lateral. All right, so let's continue. And so let me talk a little bit about the Ivic approach. So our approach, of course, is quite different. So in Ivic, he actually used a formula of Kuznetsov and Motohashi for the so-called twisted second moment. For being twisted, I mean we weight this square of the central L value by the Fourier coefficient. Okay, this is what I mean by twisted. And of course, here this H will be a very nice smooth function, or very nice smooth wave function. And then Kuznetsov proved this identity, and actually he has some errors in his proof, and Motohashi fixed this in his book, in his spectral theory of Riemann zeta function book. And it turns out to have 6 terms, and these terms are all explicit in terms of the divisor function, and also you have certain integral transforms of this H. This might have some similar with Riesmann's talk, the integral transform in Riesmann's talk, and their proof also uses the Dirichlet series and the analytic continuations and so on, and it's very explicit. And this formula is very effective. So Motohashi used it to treat the twisted second moment in one of his papers, and also in his book. And however, if you want to consider the cubic moment, if you erase the degree by 1, then you need to average over n using a approximate functional equation. All right. However, Ivic's approach using this Kuznetsov-Motohashi formula, he has some losses. So what we're going to follow is approach of Conrey and Iwaniec. I would call it Kuznetsov-Voronoi approach. So what they do is they apply Peterson-Kuznetsov after approximate functional equation, and then they did a triple Poisson. Okay, but here we're going to do a Poisson plus Voronoi instead. But the idea is essentially the same. So and the Voronoi is a generalization of Poisson, so I would call it Kuznetsov-Voronoi approach. Of course, as mentioned in response talk, so this Conrey-Iwaniec can be interpreted as an inverse of the Motohashi formula, or you can view it as a reciprocity formula. And there are lots of work on this due to Young, Petrov, and lots of people, including Rizwan and Humphreys, and recently, for the spectral aspect, recently by Kwan. Okay, so like I said, Conrey-Iwaniec treated the character twist, or you can say the Q aspect, but we are going to treat the spectral aspect. And our idea is to use the analysis of Cauchy and Young and combine their ideas. The new idea here is that we are going to use a second Voronoi. This is the idea of Cauchy, and also we are going to use large sieve. This is an idea of Young, and we're going to use a lot of analysis due to Matthew Young. And one motivation is a non-vanishing problem for mass forms. So in this case, for this problem, you need to consider the first moment, the twisted first moment and the second moment. And also you can say the modified moments. And for the mass form case, it's some results, recent results due to Liu Shenhui and Bakhanova, Huang Binrong, and Sodergreen. And their approach is to use the Kuznetsov-Motohashi formula, the same as Ivic. And this is very effective, like I said. So it's very effective when you treat the second moment. And also me and Shenqi Liu, we used the Kuznetsov-Voronoi. We had essentially the same kind of asymptotic formula. And one thing that we had is actually we were considering the non-vanished problem over imaginary quadratic fields. So, but in that case, we do not really have a Kuznetsov-Motohashi formula. So that's why we choose this Kuznetsov-Voronoi approach. And in the Maass-form case, like I said, we essentially obtained the same kind of asymptotic. And so you can say these two approaches are more or less kind of equivalent. And actually, in the holomorphic case, if you use Peterson plus Voronoi, then you can get a formula of Kuznetsov in the holomorphic case. And this Kuznetsov had this in a preprint. Probably it's very hard to find, but the paper of Bakhanova and Fourier-Hankel in JEMS, they reproduced his proof, so you can check that for the holomorphic case. One thing I should mention here is that the main term, which was very easy to see in the Kuznetsov-Motohashi formula, in our case, actually, it has two sources. One is from the diagonal, another is from the zero frequency after Voronoi. So you have two sources, they combine to get the main term. This is one thing that's kind of different. Okay, so now let's come to the proof. And essentially, I'm going to use Kuznetsov and Voronoi and then Poisson. That's the strategy. And maybe let me talk a little bit about the formula here. So first of all, I'm going to introduce the basic kernel because they're going to appear in both Kuznetsov and the Voronoi. So I'm going to define it using this notation BS. B stands for Bessel. Okay, so first of all, in Kuznetsov, you have this Bessel integral defined this way. And if you, so this integral is over this t, over this parameter t, all right? And if you remove this Bessel function, you will get, I will call it a Plancherel integral, because this is the Plancherel measure against this weight function h. This will appear in the diagonal. All right, so this is what we have in Kuznetsov. And for Voronoi, in our case, we only need to consider B0. So you take this S to be 0, and you have this so-called Hankel transform. The Hankel transform is quite different, so you can view it as an analog of the Fourier transform. Okay, actually, the Fourier transform will appear in Poisson later, anyway. So, what we really need is this asymptotic formula when x goes to infinity. I write it here. And if you again say remove this Bessel function, then you will have some meta integrals. So you have this this meta integrals coming from the zero frequency in the Voronoi. Okay, so Kuznetsov will look like this. So you have a pair of Fourier coefficients. Okay, and then the left-hand side is the spectral side, and the right-hand side you have the diagonal term and the off-diagonal term. So besides the Bessel integral, you also have this Kurzmann sum. All right, and because we are summing over all the even forms, so you have you need this to be both positive and negative. So you have plus and minus here. All right, so this is Kuznetsov, and I think an expert would recognize this immediately. And also we have Poisson and Voronoi, and for Poisson we need this a little bit generalized Poisson. So we sum over additive twist of a weight function modulo C. So here the conductor is C. Then on the right-hand side you will get a congruence condition. One thing you should note, a small comment here is that if you take this AC to be coprime, then you don't really have a zero frequency here. So if you see, when C is greater than 1, of course, then you don't really have a zero frequency. And here is the Voronoi. So you have the zero frequency and non-zero frequency contribution, the dual sum, you can say, and everything is dualized. Later, this M will denote the dual variable usually. Okay, so this is Voronoi. Okay, so now let's start the proof. We're going to proceed as in Conrey-Iwaniec. So we start with approximate functional equation. And here we're going to write it as a square, and so L squared times L. We split this cube, the cube as square times L. All right, and for the L function, it was defined like this. And if you take the square by Hankel relation, you find that you need to treat this Fourier coefficient by the divisor function. Okay. And because of this divisor function, we need to apply Poisson. And for this one, we just apply, we need to apply Voronoi. And for this one, we'll apply Poisson. And for the Riemann zeta function, we have something very similar. So anyway, so approximately, the approximate function equation says that you need to sum up to t or sum up to t squared. Depending on whether this is the first moment or the second moment. all right? And usually we need a smooth version. So we insert a smooth function here, a smooth weight function here. And this n1 and n2 will be t or t squared, up to t or t squared. And for convenience, we are going to use a version of a Poisson function equation of Bloomer. And his version is very convenient to us to get to the main term. All right. So, but of course, the main term is not our concern. We're going to mainly talk about the error term. So after a Poisson functional equation, you can reformulate it in this form. You have a average over the mass forms, and you have n1 and n2. Okay, and also we consider here the smooth version. And for the off-diagonal sum, you will get Kussmann sum here. Of course, you have this divisor function here for n2, and also you have a Bessel integral, and also I inserted some smooth function here, smooth weight function here. All right, and I'm going to, for convenience of notation, I'm going to write the whole smooth part as analytical part as this w plus minus x1, x2, and lambda. And lambda is essentially the size of the argument in the Bessel integral. All right. All right, so the main term, like I said, it becomes transparent after the Voronoi. So half is from the diagonal term in Kuznetsov, and half is from the zero frequency after Voronoi. So I'm going to skip this, and let's come to the error term. And for the arithmetic part, you start with a Kussmann sum, all right, and then you apply Voronoi. You will get a Ramanujan sum. And here, this M2 will be the dual variable corresponding to N2. Okay, so you have a Ramanujan sum, and then you apply Poisson, and you will get exponential factor like M1, M2 over C. And also, you have this coprimality condition to ensure that there's really no zero frequency after Poisson. All right, so keep this exponential factor in mind. We'll have this later. And also we have this analytic part. So for this part, we need to consider the Fourier transform and also the Hankel transform with respect to those two variables. So you can say it's a Fourier-Hankel transform of the Bessel integral. And this is a thing that we need to consider, the main thing that we need to consider here. So first of all, we have this expression due to Chacheny and Mathieu. So depending on whether it's a positive or positive real line or negative real line, you have x squared and minus x squared. I write it like this, and you will have this cosine h and sine h. So these are the only difference. And if you remember, I'm going to replace this t by k and the average over k, right? And you see that here this part is very easy. So you only have this t times ETR over pi. So these are the only two places you have this capital T. Okay, and also you can check some result of if you do a stationary phase, and you can see that this h can be it's negatively small unless you are in this range. But you don't need to, for the audience, you don't need to be concerned with this. So now we're going to analyze this Fourier-Hankel transform. So we need to consider this double integral, and also we can insert the integral form in this form into this h. Okay, so indeed we have a triple integral, and for these two integrals, we do stationary phase after Mathieu, and it turns out we can box this y1, y2, and lambda. So for this phi, I'll give the definition in the next slides. So for this phi, the variable would be simply y1, y2 over lambda. And this y1, y2 over lambda will correspond to m1, m2 over c. All right, so keep this in mind. And also, you have this exponential factor. This actually comes from the computation in the arithmetic part. And if you combine them together, you have this expression. So here are some restraints when you apply stationary phase. So anyway, so now let's give it a name. So we write it as x, and we say that x is on the range of capital X. And in this case, we can rewrite. We have this kind of definition of this phi integrals, phi plus and phi minus. You can see they are actually still very similar. Instead of, so here we have tangent h and the cotangent h. So they are kind of very similar. And here we also have this weight functions. So we have this v plus and v minus, and this v plus v minus have this turns out to have this support. They are supported on some parameter u plus and u minus over t. So these are the support of this v's. This is actually very important. And these parameters are given by this. And for the audience, you don't need to know explicitly what this u plus u minus are. So anyway, and also you have this kind of conditions. And again, this you can ignore this. And all you need to know is that this u plus and u minus are up to t over m. Okay. All right. So these are essentially what we have for the Fourier-Hankel transform. So it turns out to be this phi plus and phi minus integrals. And now I'm going to say a little bit about the unsmoothing process. So if you recall, what you need to do is that you need to replace this capital T by capital K, and then average this K over T minus H and T plus H. All right. So this is what we had in the unsmoothing lemma. And now we pull out the part with this T. So one part is in the exponential factor, and another part was here. Okay. So essentially, we need to average this K times EKR over pi. And you can just do integration by parts. And so let's only consider these two terms. And the remainder will be actually similar. So in the numerator, it's again K times EKR over pi. So this is not changing, really changing. So the only thing that's changing is like we need to divide it by R times M, okay? And R, like I said, has a support. It's supported. R is supported on essentially U plus minus over T. All right. So roughly speaking, so you are losing a T over mu when you apply this averaging process. This is the loss that we have. Okay, so just keep this in mind. And like I said, you don't really need to know what this U really is. And finally, by Manning technique, so you need to do something before the large sieve. So this is due to Matthew Young. So essentially speaking, this phi integral can be written as this T integral, this Manning integral, and you have this some kind of lambda of T. And this is also not important because as long as you know it's bounded. Okay. And and one thing that's important here is that this t is supported near this u. Okay, this is the support of the integral. Okay, now let's come to the final stage. So after approximate functional equation, Kuznetsov-Voronoi and Poisson, and everything that Xiaoqinli and Matthew Young has done. So we will arrive at this expression. Okay, so you have the sum over C and the sum of the dual sums over M1 and M2. And the important thing here is that you have this free integral with argument M1, M2 over C. All right. And then we insert the mating expression here, and then bounded by absolute value. And in that case, we can just ignore this lambda. All right. And then we will arrive at this kind of expression. So here you have C sum, M1 sum, M2 sum, and they will correspond to this SC and SL and S natural L. And they are defined essentially by this kind of Dirichlet polynomial. It's, roughly speaking, it's kind of defined by this. Okay, now what we do is that we do a dyadic partition. All right, so this is what we already done, right? Yeah. And you have this some conditions, and the U and will be look like this, but you can just ignore this. All right, ignore all of this. So, and then what you do is do Cauchy-Schwarz, and then you will have this kind of expression. So you have square root of two integrals. And now we are going to consider, so we have two main actors. One is the length of summation, and one is the length of the integral. All right. And one thing that we're going to do is that we're going to do a second Voronoi. And for this second Voronoi, we will go from, say, if on one side is length n, then on the other side is the dual length. Okay, you have essentially the same expression. And you know that the dual length is like t squared over the original length. So you can always reduce the length to at most t. So if n is greater than t, then you use this Voronoi, and if it's not, then you just use it as is. So anyways, you can always reduce the length to be at most t, and the t, like I said, is roughly u plus minus. This is the length of the integral. So you can always, roughly speaking, you can always reduce the length of summation to the length of integral. This is what we do. And for the other part, you can actually check the length of summation is already less than u. So you don't need to do anything in that case. And now we use large sieve by Gallagher, and you can essentially speaking, this you have this sum. This sum is you can say Dirichlet polynomial, and you just integrate it over t, and then you have this expression. And if you recall, this an is roughly speaking 1 over square root of n, roughly speaking. So the bound in our case will be the length of integral plus the length of summation, roughly speaking. And you can always use the second Voronoi to reduce the length of summation to be smaller than the length of integral, right? And now we apply this Gallagher's large sieve, then this is bounded by the square root of u and square root of u, bounded by the length of integral. All right. And if you you can then write it as this m times u. this is what you get after everything. Okay, and the final step. So if you consider the smooth version, and we recall that this U is bounded by is up to T over M, right? And this expression then is bounded by T to the 1 plus epsilon. Okay, so this is a smooth version. Usually this is easier. And for the unsmooth version, if you recall that we lost this T over MU when you do the unsmoothing process. So in this case, it turns out that the law, so you multiply this by the loss, then it turns out to be also T to the 1 plus epsilon. So no matter what this M is. So actually the M will be chosen to be T to the epsilon, as small as T to the epsilon. So anyway, so we can, in conclusion, we always get error term of size T to the 1 plus epsilon, both in the, actually in every cases. So for both the non-interval version or the shorter interval version, and also the unsmooth also the smooth version. So anyway, so this is my talk, and maybe I add something. So maybe something something here. So in our case, as Rizwan mentioned in his previous talk, so he considered like GO2 times GO3 in one of his case. And if you take the GO3 to be Eisenstein series, then you have this cubic moment. Okay. And later in this conference, Lindelof Xiao will present a similar result for the GO2 times GO3 case, and using similar ideas. Okay, and so everything is kind of similarities. So so anyway, so maybe our result can be deduced from Rizwan and Peter Humphreys formula, explicit formula, with some work on the integral transforms. So, but here in our case, the integral transform has already been studied by Matthew Young and Xiaoqun Li. So everyone is at hand. So anyway, thank you. That's the end of my talk.
Thank you for the nice talk. Are there questions from the audience? Yeah, you mentioned Matt Young's treatment of stationary phase. Which paper is that of Matt Young?
Oh, sorry. Yeah, this paper, the JEMS paper, Matt Young.
Ah, okay. So
essentially speaking, he obtained a hybrid wild type round. So in both the T aspect and the spectral aspect and the Q aspect.
Yeah.
Yeah.
Okay. Are there further questions from the audience? Can also be asked in the chat or online. Okay. Seems to be not the case. Then, yeah, let's thank the speaker again. Thank you very much.
All right, thank you.